Hello and welcome back to Calculus 1, section 4.9, Antiderivatives, i.e. integrals. So we are familiar with the fact, I hope, that the derivative of x squared is 2x. This lecture is about to reverse this, and it's going to say that the integral, or the antiderivative, of 2x dx, that's the notation, is x squared. Now, there's more to that, but let's leave it there for now. There's some plus c that we need to put in. So the notation used to be the derivative of, and then you put function inside these brackets. The new notation now is integral, sine, and dx. You can't skip any of the two. Both of them are together, one notation for the entire thing. Now, I told you there is more to this. What is the derivative of x squared plus 10? 2x. And if I integrate 2x, I'm going to get back my x squared, right? So you see that in this case, yeah, it was plus 0, so no harm done. But in this case, it's plus 10, and definitely harm done, right? Because I didn't get plus 10 back. See, derivatives destroy that piece of information, because the derivative of any constant is equally 0, and whatever constant you had there is gone. And integration, or antiderivatives, cannot retrieve that just by looking at the, right? Because what happens if I ask you, what's the integral of cosine x dx? You know what this is, right? Sine x. But then I'm going to say, you're wrong, because what I thought of was sine x minus 5, right? You see that? So this is the reason why you are going to put plus c, and then I can't come up with that thing, oh, but I was thinking of sine x plus 5, because that plus c will take on whatever value needs to be there to have the derivative side satisfied. So now we are going to learn 0 new formulas, because you already know derivatives, which means you know integrals, because they're backwards, right? If you say that the derivative of a constant is equal to 0, then the integral of 0 dx is going to be 0 plus constant c, which is just c. And yay, there you go. You got your c back. The only one that is different, you have to do some algebra and manipulations to get to this point, but x to the n. You know there was n x to the n minus 1. Now what I'm going to do is I'm going to shift all of this into integral of x to the n dx, and say it's x to the n plus 1 over n plus 1 plus c. So if I integrated this, I would get xn as the answer. But I'm integrating xn, so everything is shifted by plus 1. Now, for those of you more interested in mathematics, I would challenge you to sit at home and just, pound on this a little bit to get those formulas to match like everything else on the chart. What is the derivative of e to the x? So what is the integral of e to the x dx? Plus c. Yes, plus c. What is the derivative of ln x? 1 over x. So what is the integral of 1 over x dx? ln absolute x plus c. Well, so there's this absolute value that it's new. See, not too much stuff is changing here. How about the derivative of sine x? Very good. So what's the integral of cosine x dx? Nice. I'll put 3 dots here, and I'm just going to pull another one because you know all 6. Derivative of cotangent. What's the derivative of cotangent x? Negative cosecant squared x. Very good. So what is the integral of cosecant squared x dx? Negative cotangent x plus c. Yeah. So that negative is either on the left or the right. You can move it as you need it. So there you go. Right? All of these antiderivatives.
Any advice for not turning the integral into an f every time you write it by accident because it's just muscle memory?
Just write integral 15,000 times. By the time you're done with your education, it'll be irrelevant anyway.
I've had to scribble out every one I've wrote so far because I put the line through it for the f.
For each one of them, right? They all look like this.
Because my muscle memory just kicks in, you just put it there and you're like, shit.
Yeah, life. So we know all the integral formulas. The one that you have to work on is the one for polynomials, right? So if your derivatives subtracted 1, integrals are going to add 1. And that's it. There's also this issue with absolute value with ln. There is the issue of the domain. This ln x domain is, as input, is 0 to infinity. 0 to infinity. And this one is negative infinity to 0 union 0 to infinity. So whatever you plug in on the left, you can definitely plug into the right because the domain on the right is bigger. Now those roles are reversed for integration. And if you don't put absolute value, well, you can compute negative 1/2 on the left, but you can't compute negative 1/2 on the right because of the domain. So we put absolute value and then you can compute. So it's those absolute values are not there for decoration. They're there because we actually need to be able to compute things. Integrals will be dealing with accumulation. We'll see that in chapter 5. So it deals with stuff like energy and fields and so on, and we need to be able to compute those, even if they're negative. So ln over there with absolute values. Yes.
So the ln, for example, ln 2x, we also get 1 over x, right? So,
Yes.
so for the antiderivative of that, it's going to be ln 2x in the absolute sign or just x?
Just x. Yeah. Because there is this plus c that you can write as... no. We'll deal with that. We'll deal with that when the example comes up. If you write it down, we'll deal with it. We have to write more formulas now. Now these formulas are important. So integral of f plus g dx is integral. Here's me doing the same thing like you.
No, I fixed it.
Integral f of x dx plus integral g of x.
It's just a long s.
Actually, that's true.
You don't put a line through a long s.
Yes. Integral sign is long s. And we'll see that why in chapter 5. The old notation, I believe, used to be like this. Original Riemann notation or something like that. This is S. Stands for the sum. I think that was the notation, or maybe UP. Something like that. Anyway. Doesn't matter. So if you have integral of two functions that are either added or subtracted. So I'll add the minus sign now underneath. And then if there is a constant, yeah, we kick C in front of the integral. You know that the same rules were there for your derivatives. If you have multiple functions added, you do derivative on each separate one, and if you have the constant, you can kick constant in front of derivatives. You do the same thing for integrals. You remember that the derivative of a product has a product rule to it, right? Well, for integrals, it's the same thing. Special things are happening when you have multiplication and division. So you can't, if you have an integral x e to the x, you can't just integrate each one separately and multiply. That doesn't work. X e to the x is actually solved in Calc 2. You learn a method called integration by parts to solve that one, which is the product rule derivative thing. So these are the only two rules that we are observing right now, that if you have a multiple functions in the integral, added or subtracted, you can deal with each one separately. And if you have a constant in front, you can kick constant outside. And now all we need to do is 5,000 examples. And if we get the chance, we'll also calculate value for C. You can calculate C if you get something that's called initial condition. The first order of business is to integrate, let's say, 3x to the 5 dx. So I am going to kick 3 in front of the integral and just focus on integrating x to the 5 dx. Now, that is clearly our rule, which we had over here, where you take this n, which is 5, and you go +1 and +1. So this has to be x to the 6 over 6, and then we put this plus c. You always have to put plus c. Remember that one. Problem solved. The integral of 3. Oh, I forgot my 3. There's a 3 there. So they cancel down to a half. So x to the 6 over 2 plus c. I forgot to copy the 3. Integral of x squared plus 4x minus 9. Observe that I'm using parentheses if I have multiple terms. I did use parentheses here as well when I defined, when I show you the rule, because all of this is actually times dx. There is a times there. Now, it doesn't make any sense now. It will make sense in 5.1. Right now, from notation point of view for your next exam, know that there is multiplication there, which is the reason why we need these parentheses. All of this is one thing times dx. If you don't put parentheses, obviously notation is wrong. If you don't put dx, then just the whole thing has no meaning. Now, you can break this into 3 integrals in steps, or you can just integrate one at a time. It doesn't matter. I'm going to break everything into steps because we are looking at this for the first time. I'm kicking all the constants outside. Observe that each integral has its own dx. And observe that the last integral just has integral dx. Well, there's number 1 in there, but So first one is x cubed over 3, because n is 2. 2 plus 1 is 3. So maybe I should, that's the only rule that is different than derivatives. So I'm going to write it on a board. Integral x to the n dx is x to the n plus 1 over n plus 1 plus c. That's the only one that is different. So now when you look at that square was there. That's a square. So 2 plus 1 is 3. 2 plus 1 is 3. So n cubed over 3. Going to the next term, exponent is 1, 1 plus 1 is 2, so plus 4x squared over 2. Minus 9, and over here, you have 1, and 1 is x to the 0. Plus 1, it's x. And plus c. So if you have x to the 0, which is 1, which is in that integral there, integral dx, it's integral 1 dx, x to the 0, so if n is equal to 0, then 0 plus 1 is 1, so you have x to the 1, divided by 0 plus 1 is 1, so x to the 1 over 1, which is x. So that's how you get negative 9x. And now 4 and 2 cancel. And the answer for this, you can write 1/3 x cubed if you want to, plus 2x squared minus 9x plus c, and that takes care of the problem. Integral of 4x cubed minus cosine x dx. Tell me, what should I do? What? Okay, we can split, sure. So 4 integral x cubed dx minus the integral cosine x dx. So you kind of see that this dx distributes over both, right? So what's the first integral? Good. And then what's the integral of cosine x? Sine. Plus c. 4's will cancel. You do not have to write this step at all. It's not going to give you or take away any points on the exam or something. You know that that term is that term, this term is this term, you have plus c, so you can go directly from the first to the third line. Integral of 4 times cube root of x dx. So we kick 4 out, and we write x to the 1/3 dx. So 4, and now it is x to the 4/3 divided by 4/3 plus c. Simplify double fraction. Well, 4 and 4 will cancel, and we have 3x to the 4/3 plus c. There is a formula that the book wants you to memorize, but then we'll take care of this formula when we get to chapter 5. They want you to memorize that e to the ax dx is e to the ax over a plus c. So that's a modification. So you can deal with e to the 3x. And then also for trig, all of trig. If you have integral sine of bx, let's say, dx is going to be negative cosine bx over b plus c. So if you remember, you used to multiply chain rule into your derivatives. For integration, you are dividing by those numbers. So just to contrast these quickly, derivative of e to the 4x, right? The derivative of this was 4e to the 4x. Now, integral of e to the 4x dx is equal to e to the 4x over 4 plus c. See? So for derivatives, we multiply because chain rule. For integrals, we will divide by that 4. Now, integration is much trickier than derivatives. Derivatives are really straightforward. When you learn the rules, you can take the derivative, and better off, you can always take the derivative. The integrals are far more sinister because there are certain functions that cannot be integrated at all. Everything can be differentiated. If you put anything on a paper, you can differentiate. Derivative might not exist at one point, right? Because it's spike or it's cusp or vertical asymptote, sure. But write any kind of function on a paper, whether it's explicit or implicit, you can always hit it with a derivative and solve it. Not the case for integrals. Integrals are much trickier. We have a whole bunch of rules, and then we still can do a whole bunch of them, and we use numerical methods, which we learn in chapter 5 and chapter 7. Now, the good thing for integration is that if you're not lazy, you can check your work 100% of the time by simply taking the derivative. See, if I want to know if this thing is correct, right? Is this good? Maybe I shouldn't be doing that because I wanted to show that. So let's take a look at another example. Say integral of tangent. Can't do tangent. Integral of secant 3 theta tangent 3 theta d theta. This is the, right? So now you see it's a 3 theta there, right? It's 3 theta, 3 theta. So there is that modification of bx, right? B times x, b times theta. What is the secant tangent for the integral goes into? Which one? I.e., which derivative would produce secant tangent answer? Secant. So this has to be secant 3 theta and by the formula we had up there, divided by 3. And now you ask yourself, so you have to think backwards now. And now you ask yourselves, is this correct? Well, check procedure. The derivative in respect to theta of secant 3 theta divided by 3. We know we have to copy 1/3. That's the constant. And what's the derivative of secant 3 theta? It's a secant 3 theta tangent 3 theta times 3 the chain rule. There they are. They cancel, and you got exactly what you were supposed to get. Secant 3 theta, tangent 3 theta. So that was the aspect of the integration that I absolutely loved as a student. Because I know that every integral I do is 100% right. All I need to do is to take the derivative. If I get this, good to go. If I get something else, it's definitely wrong. There's no gray zone, right? Where you can say, oh, well, I really don't know. You either get it or you don't. Definitely. What's the integral of 5x to the 8 minus square root x dx? Well, we rewrite this, right? 5 integral x to the 8 dx minus integral x to the 1/2 dx. And now we solve it. What should I write? What should I write? 5. Copy the 5, right? We know that by this rule. Over here. See, that's kicking out 5. You kick 5 in front of the integral. So you want 5x to the 9 over 9. Very good. So 5 x to the 9 over 9 minus 1/2 plus 1. Come on, that can't be that difficult. 3/2, yes. So x 3/2 divided by 3/2 plus c. So it's either going to be plus c or minus 1, whatever. Anyone? Yeah, you got it. What do I mean by plus c or minus 1? If I say plus c or minus 1, what do I mean? Yeah. If you don't put plus c, you get minus 1 on the test. Your test has 10 integral problems. That's minus 10, the letter grade down.
But with those 10 problems, if you just go and write plus c,
Let's see, 1 point.
that's 1 point each.
Exactly.
You at least get 10 points in that.
Hell yeah.
So 10 plus 7 quizzes, right? So you're guaranteed 17. Yeah.
Boom. Done. Drop mic, we're out.
So how do you know x to the 9 is from the formula?
Well, the formula is your input is 8. So 8 plus 1 is 9. 8 plus 1 is 9. Or to answer the way my teacher answered, how do I know? Like this. Oh, no.
Sarcasm.
Minus 2/3 x 3/2 plus c. When I took this the first time, you actually, if you want to do well at all in class, you actually have to do these problems on the board in front of everyone and discuss things like this. Right? So this teacher actually was so annoyed with one student. He drew a line on the chalkboard on the floor and told him, "You do not cross this line ever." That means 0 in the class, because most of your grade is there when you go and you do the problems. And then one occasion, we all agreed in the class, right? When he asked who wants to do this problem, no one answers it, right? And only the guy who's not supposed to come to the board. So he forgot about that, right? and he called his name, and he was whatever was doing, and the student goes like this. Can't reach it. And then teacher is like, so? What are you doing? This is the line. Yeah, lots of fun. Lots of fun with integration, guys. Let's take a look at few examples from the textbook since we have plenty of time. Questions, it's like 7, right? You're going to love this. Remember, step number 1, rewrite, so get it in a form that makes sense. Integral, open parenthesis, 3 over x to the 4th plus 2 minus 3 over x squared dx. The way I'm going to rewrite this is 3 is the constant, gets kicked out in front of the integral, and I have x to the minus 4 dx. Plus 2 gets kicked out, and we just have dx, so that's that situation where we just get x, right? And then minus 3, integral of x to the minus 2 dx. So we have, we just take all of the exponents, bring them up as negatives, and now you do plus 1. So 3, x to the minus 3 over minus 3, plus 2x, right? When you have, maybe I could add that to a list, I don't know. Minus 3, x to the minus 1 over minus 1, and then plus c. And now you fix everything to look nice. 3 and negative 3 cancel, so we have negative 1 over x cubed plus 2x. Negative and negative is positive, so plus 3 over x, and then plus c. Now, I'm not picky about it. Some others might. You see, when you are looking at this expression, you can put it in the decreasing order of powers, right? So this is the highest, and then the second highest, and then, right, the third one. So as you look at that, it's equal to 2x plus 3 over x minus 1 over x cubed. It's not necessary at all, but cool. Now, I wanted to leave the 2 minutes at the end just to discuss this very quickly and briefly. What is this? Right? So we know that plus c needs to be there. But the question is, can we compute the value for it? So in order to compute c, we need what we call initial condition. Now you might be asking, well, what the hell is initial condition? Initial condition is a point in space. Maybe I should say point in space, fine, whatever. So now, say that this problem here, we found that f of x is equal to 2x plus 3 over x minus 1 over x cubed plus c. And say now, let f of 1 be 2. So this is initial condition. And this is what's given to you. So you get the integral and you get the initial condition. If you get the initial condition, you can compute c. It's done, simply just plug it in. I'll write even the word just. Just plug in. So f of x is replaced by 2. On the other end, you have 2 times 1 plus 3 over 1 minus 1 over 1 cubed plus c. You see, the entire equation is just c is the unknown. So you have 2 equals 2 plus 3 minus 1 plus c. And the answer is c is negative 2. So the actual f of x is equal to 2x plus 3 over x minus 1 over x cubed minus 2 when you plug in. And those of you who are looking for verification of, visual, what's happening? If I say that I want to integrate 2x dx and I get x squared plus c, what do I get? X squared plus c graphs as, we know what plus c, what does the plus c do? What is this plus c going to do to this graph? Move it up or down. So technically what you get when you have a plus c is you get the family of infinitely many x squares. And then you have infinitely many of them. And if I pick a point in space, which I call initial condition, there is going to be exactly one of these that goes through that point and none of the others. You see that? So when I give you x squared plus c or whatever other integral we did today, you are stacking infinitely many, graphically, right? You're stacking infinitely many of those on top of each other. If I give you a point in space, exactly one goes to that point. And that's the one that you compute. So I give you x and a y, you plug in all of your x's, you plug in y, which is the entire integral equal to that, and the only variable you have is c. So you solve the integral, right? And when you get the answer on the bottom, you can compute that c only if you have initial condition given. And if you are confused on what initial condition is, well, let's say you're going to make a turkey. All right? Initial condition would be a temperature of a turkey after 30 minutes of baking. So you put the turkey in the oven, and after 30 minutes, you put it out, you stick a temperature probe in it, and you know the T is 30 minutes, and then the temperature is, let's say, 80 degrees.
How small is this turkey?
Well, maybe you left it to thaw out, so it was going in on a room temperature of, let's say, 68 degrees. So 30 minutes later, still 80 is too much, but whatever. There are some really cool calculations you guys can do with that. So that ends the lecture. We don't learn new formulas apart of this one. Looks kind of new. Everything else is backwards from derivatives. And don't forget the plus C. If I give you the value of the initial condition, you can compute that C. I will see you on next Saturday at 10.